Part C.3, Insertion sort. Now we are ready to complete the whole insertion sort. It is very simple. We just put all the insertion steps together from beginning to end. We have the insertion sort. All right, so let's look at it. Because the procedure is pretty straightforward. So we do not even need to really go through the details. Here, let us just do the estimate efficiency. Because when we do it, we automatically go through the whole insertion sort. When we do it, we look at this operation, compare and shift operation, because each step we need to do comparison first. Then, based on the comparison result, we make our decision. Should we do shift operation or we stop? Because we do not need to do further operation. We can stop. Two cases. All right. So then let us use this diagram to do the analysis. So this is the general case insertion step. All right. So the first time we do comparison. All right. Last two elements we do comparison. If AK minus 1 is greater than AK, then we do the shift operation. How to do shift operation? We copy AK to a temporary location, then copy AK minus 1 to AK location, original AK location. Then we look at the next two elements, AK minus 2 and AK. Comparison, shift, comparison, shift, and so on. So that is the basic way we do for the insertion sort. Now we are ready to do worst case efficiency, best case efficiency, and average case efficiency analysis. First, worst case efficiency. So that means we should do compare and shift operation from the last element to the first element. We should not skip any element in the middle. We just go through all the elements. That's the worst case. When we do that, let us count the number of comparisons. Because number of comparison and number of shift operation, 1 to 1, right? We just count number of comparisons. All right. From the second element, then we do one comparison, right? Then when we insert the third element, we do two comparisons and so on. The last element, for the worst case, we do n-1 comparisons. All right, so the total number of comparisons for the worst case, this expression. This expression. The worst case. So you can see the asymptotic notation, big theta of n squared. So we can skip that 1/2 coefficient. Next, best case efficiency. This time, we want to look at the minimum number of comparisons in each insertion step. All right. We start from the last element. So you can see after we do one comparison, then we stop. After we do one comparison, then we stop. That's the best case. All right. So you can see for each insertion step. Then, when we do one comparison, then we stop immediately. So we go to the next insertion step. One comparison, stop immediately, and so on. Yeah. So you can see we do all the way for all the steps, and the total number n-1 steps. Because the first element, we do not need to do anything. Yeah. So starting from the second element, then we need to do that insertion operation. Yeah. So that is, we need to do total n-1 comparisons. Yeah. And a no shift operation. In this situation, there is no shift operation. All right? Yeah. Okay. So the asymptotic notation, big theta of n. So you can see much better than the worst case. Worst case, big theta of n squared. Best case, big theta of n. Yeah. All right. And here you can see this best case corresponds to increasing order case. So the array is in increasing order case. All right. The worst case, you can see decreasing order case, right? Decreasing order case. Yeah. So you can think about that. So the decreasing, yeah, the larger, you start with largest element. Then second largest, you have to do comparison. Then the next, yeah. So you can see this case corresponds to decreasing order case. Okay? Yeah. All right. The last one, average case efficiency. Yeah. Average case efficiency, here I just give you the result, big theta of n squared, but the coefficient will be 1/2 of that worst case. So actually the coefficient 1/4 n squared plus some minor terms. Yeah. If you want to try, you can do it. You know, practice as a example. Yeah. Remember, I talk about average case efficiency for the general insertion step in the previous video. Yeah. You can use that formula here. Yeah. Then you add up the number of average case efficiency number from beginning to end, then you will get this, this kind of result. Yeah. All right. I leave it as an exercise for you. Yeah. Yeah. But at some point, if I have a chance, then I will, show you the details. Yeah. All right. Yeah. Next. Yeah. Finally, after we have everything we need, then I want to talk about one special property for the insertion sort. So there is a very interesting special property for insertion sort. So that property is, all right, so look at this. All right. If the given array is almost sorted. Almost sorted. So what's that? Almost sorted. Then the insertion sort is a good choice of sorting. So under this assumption or condition, you can call, under this condition, it is a good choice, or we can even say the best choice for all the sorting algorithms we have, insertion sort. Yeah. But what is the almost sorted, this condition? Yeah. I can use another way to describe it. Well, we can use this. That means there are small number of inversions. Okay, small number of inversions. Yeah. Because if there is zero inversion, it's sorted. But here, because already sorted, that is too simple. Yeah. So we consider the case not sorted, unordered, not sorted, but very close to sorted. Then that means the number of inversions, that number relatively small. Yeah. In that situation, now let us look at this diagram. Yeah. So let me draw this line representing a given array. Then at some scattered location, look at these circles. Let us assume there are some clusters here. Clusters. In each of the clusters, the elements out of order, out of order a little bit, So that's the typical input. In this situation, then the best sorting algorithm is insertion sort. Otherwise, if it's a general input, then we will see it's not the best. Because for the general case, big theta of n squared, definitely we're not satisfied with this efficiency. Later you will see we can get the best possible solution is n log n. That is our goal. So we have several algorithms we can get that kind of efficiency. All right, so we finish this C.3, but we have some time. I want to work on a special sorting algorithm. In our last video, C.4, sorting a 4-element array. The reason I use that example because we need to use this insertion sort idea a little bit. So that's a good example for this topic, insertion sort. All right, so let me finish C.3 first.